Hello, ladies and gentlemen. I'm going to take some time to go over the review with you guys. So if we start at the very beginning, we had a experimental setup where this girl wanted to see which light would make them grow better, and her hypothesis was that green light would make the plants grow better. And then we have our data down on this data table right here, and that's what we need to go off of. So the independent variable, what we are changing is going to be the color of light. So whether it's white, blue, or green, or no light, in a closet, the no light would be our control. But out of those different colors of light, which one would make it grow higher? And we're using height as an indication of survival, apparently. So what's the independent variable? The kind of light. The dependent variable, what we're going to be checking to see if it changes, is the height. Two constants that we were told were age and height, approximately the same age and height. You could have put other ones, like the temperature should be kept the same. There are so many different ones that could be chosen. I just chose one straight from the text, so the starting height and the same age of the plants, because you don't want to compare a really old plant to a really young plant, because that's not comparing the same variables. And what's the hypothesis? Her hypothesis is that the plants will survive better in green light. So when we're doing a claim evidence reasoning, our claim is going to be just stating very clearly whether we agree or disagree with the hypothesis. So her hypothesis was incorrect, and we need to say why. We need to give evidence. So I'm pointing out the green light did not grow the highest at 16 centimeters, and I'm citing what its height is. Red, which had 22 centimeters, and white, which had 30 centimeters, were higher. That's pretty good evidence to bolster your claim. And now we're going to tie it together with reasoning. What I like to do with the reasoning is I like to point out what we would have seen had the other event happen. In other words, her hypothesis was incorrect. What would we have seen if it had been correct? That's a good way to put contrast on correct and incorrect. Sort of like if your parents say, hey, clean your room, and you said, I did. Had I not cleaned my room, I would have had more stuff on the floor than prior to, or I would have had the same stuff on the floor prior to you asking me to do that. So that's good reasoning. So I said if green had survived better, it would have had the highest height. So I'm giving my reasoning. All right, so for these conversions, we just have to use this to hop either to the left or the right to tell us which way our decimal place is going. So for the first one, I'm starting off with the prefix kilo, which will be right here. And I'm trying to get to grams. And if we look here, there's nothing that starts with grams, so we're just going to understand that it's our base unit. So this would be gram here, decagram, hecto, and kilograms. So we're going to start with kilo, and then we're going to hop over to grams. So kilo, 1 hop, 2, 3. So that means we're going to hop 3 times to the right. So I'm going to write out my 1 with the decimal point, and then I'm going to do the hop to the right 3 times. 1, 2, 3. And then I'm going to fill in those baskets with zeros and then move the decimal point to the right 3 times. So 1 kilogram should equal 1,000 grams. Next one we're going to start with is 5.44 liters. We're going to hop to the right as well because we're starting off with our base unit, which is liters. And then we're going to hop to the right 1, 2, 3 for that. So that's going to give us 5,440 milliliters. Now here we're going from millimeters to decimeters. So milli is here and deci is here. So we're going to have to hop to the left 2 times. So that means I am going to end up with 5,670.90 decimeters. For this next one, we're starting with centi. So we're starting right here, and we're going to hop to hecto. So 1, 2, 3, 4. So that means I'm going to put 1, 2, 3, 4 zeros in front and then go 0, 0, 2, 3 hectograms. Hopefully I did that right. Centi to hecto. Oops, I hopped the wrong way. One nice thing about this is I can make mistakes and you guys can see me make mistakes. So centi to hecto, 1, 2, 3, 4 hops to the left. No, that was right, Aubin. 0.00004 times 0, 2, 3. Or if you wanted to put it in scientific notation, which would make more sense actually, that'd be 2.3 times 10 to the 1, 2, 3, 4, 5, 6 to the negative 6. And for this last one, we've got centi, and we're going to go to kilo. So we're starting off here. We're going to go over here. We hop 1, 2, 3, 4, 5 times to the left. Ooh, these are getting really small. All right, so that's what your answer should be for the kilometers. And let's just do some logic here. We're going from a smaller unit to a larger unit. So of course the number is going to get smaller because a certain percentage or a certain proportion of a kilometer, which is a very long distance, is going to be much smaller than the actual unit. That was a crappy explanation, but let's see, convert the following to standard notation. So whenever you see these, what they mean by standard is without the exponents. So what we want to do is take our 8.6, and it says times 10 to the fifth, and that's a positive fifth. That's a positive exponent here. We don't have a negative one. The next one's going to be a negative one. So that means for this that we've got to take our 8.6 and hop it to the right 5 times. 1, 2, 3, 4, 5. Fill in your basket. 1, 2, 3, 4, and then write it out. So that'll be 8, 6, followed by 4 zeros. So this would be 86000. And I like putting commas in for a big number like that, so I can tell it's 860,000 easier. It's up to you. All right, for this next one, we're going to hop the decimal point to the left because it's negative. So to the left 3 times. 1, 2, 3. Fill in your basket. So then this number will be 0.0010. That decimal point there. For this one, we're going to hop to the right 6 times. So let me just write this number out, and then I'll just hop it in my head. So we went 1, 2, 3, 4, 5. So we need to put in one more 0. So it should be 440,030. So this number, we're going to be converting to scientific notation now. So what I like to do with these is, write out the right number, Patrick. Put the decimal point where it's starting. So the number 3,900, its decimal point starts right at the end of the number, of course, because it's a whole number. So what we need to do is make this number a number between 1 and 10. So we're going to do that by hopping it to the left 3 times. So since we had to hop to the left 3 times to make this number 3.900, that means that we're going to be giving it a positive exponent. So we had to hop it 3 times, so we'll write that to the third. And check it if you want. If you look at that number and you take your 3.900, this says to the third right here. So let's hop it to the right 3 times. 1, 2, 3. That'll give us 3,900, and that checks out. For this one over here, we want to make this a number between 1 and 10, so that's going to be 2.8. And to do that, I had to hop 1, 2, 3, 4, 5, 6, 7 times to the right. So I'm going to make this times 10 to the negative 7. For this one here, we're going to have to make that big number a number between 1 and 10. So I'm going to take 6.149 followed by 4 zeros if you want, times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. Oh, I didn't even see these cut out down here. So for this one, it'll be 0.000210009. For this one, it'd be 1.1200 because anything times 10 to the 0 is itself. For this one, we'd make it 4.0 times 10 to the 1st. And for this one, we take 4 times 10 to the 0. All right. Next one is asking us to identify whether something's an atom or an element, identify how many of each they have. In this first one, we've just got one hydrogen atom and just one element, which is hydrogen. So the lowest number you could have for any of these is 1. For this one, it looks like the number of atoms is 1, 2, 3, 4, 5, 6, 7 from what I can see. 7 atoms. And how many elements? I see a red one, which, by the way, is hydrogen, a yellow one, which is sulfur, and a white one, which is hydrogen. So I see 3 different elements. You don't need to know the colors. I'm just telling you. For this one, the number of atoms would be 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm only seeing 9. Technically, there may be a hydrogen hiding there, but from what we can see, there are 9. And as far as elements, there's carbon, hydrogen, oxygen, so 3 as well. This one did not format well, so I'm going to cross it out because there was a larger something happened with the formatting, and it didn't show the whole structure. This one, to figure out how many atoms, we have to add up the total number in those subscripts. If it doesn't have a subscript, it's assumed to be 1. So we have 8 carbon plus 9 hydrogen, which would give us 17, plus 2 oxygen, which will give us 19, plus 1 nitrogen, which will give us 20. 20 total atoms. How many elements? Well, we've got carbon, hydrogen, oxygen, and nitrogen. So that'll give us 4. For this one, for number of atoms, we've got 1 magnesium and 2 bromine, so that'll give us 3 atoms. And the total number of elements in here, we've got magnesium is 1 and bromine is 1, so we've got 2 here. For number 8 here, we're going to look at the picture and circle whichever ones that apply. So looking at this is a pure substance. It's not a mixture. If it were a mixture, we would see something like this, where particles are different from each other. Here, this particle, which is a square circle, is identical to this, which is identical to this, which is identical to this, which is identical to this. So it's a pure substance. So because it's a pure substance, it cannot be a mixture. And it cannot be an element because we have compounds put together. In other words, we've got different elements bonded together, so it can't be an element. As far as it being a molecule, we have molecules in the mixture, in the substance. So the substance is a molecule. It's made up of molecules. And the substance is also a compound. Remember, if something's a compound, it's definitely a molecule. All compounds are molecules, not all molecules are compounds. So when we're looking at this second picture right here, this can't be a pure substance because it's a mixture. We've got different type particles in there. So we've got a mixture, and it can't be an element because we don't have just one type of element in there. It can't be a molecule. We don't consider these molecules because it's a mixture. It's a mixture made up of different molecules, but the substance isn't just one thing. And the substance also has compounds in it, but they're different compounds mixed together. So we're not going to consider this a compound. We would only really use these terms if it were pure substance. Once you've got a mixture, that's pretty much where you stop. So let me erase this in case you guys think it's an answer. For this next one, this is definitely a pure substance. We have particles of only one type. Therefore, it cannot be a mixture by definition. That's like saying if you have a frog, it's the same thing as a human. It's not the same. A pure mixture is a totally different. It's the anti-definition to a pure substance. So if you have a pure substance, it's the anti-definition to a mixture. This would also be an element because we only have one type of element in there. It couldn't be a molecule because, well, we have only one atom not bonded to anything else, and it can't be a compound because we only have one element and the atoms aren't even bonded to each other. So if it's not a molecule, it's definitely not a compound. For this last one over here, this is definitely a pure substance because we have particles of the exact same type. So I'm going to circle pure substance. So by definition, it cannot be a mixture. So it's not a mixture. It's definitely, we can call it an element because each one of these are made up of the same element. That's the same thing as saying if we have H2. Yes, it's an element. So let's circle element. Is it a molecule? Well, yes, they're molecules of the element because we have more than one atom bonded together. So it's also a molecule. Now, is it a compound? No, it cannot be a compound because we have the same types of atom in each particle. We have the square and square. Now, if we had something else like this square circle over here, okay, that's a compound. But in this example, this does not have a compound in it. So for number 9, it says, based on the two images, identify whether they're hetero or homogeneous. Homogeneous is usually an evenly mixed mixture, of course. So you can't see the different phases. So salt water is a good example of a homogeneous mixture. And this one, A, is a homogeneous mixture. Just remember homo meaning same, that it looks evenly spread throughout. So then this one is a heterogeneous. So an example of a heterogeneous mixture would be like oil and water. On these, you need to label element, molecule, compound, homogeneous, or heterogeneous. So I'll tell you the hint. If there's a mixture, we're going to see a plus sign in between something like soil and water. If you see a mixture, or you'll see the ampersand. I can't draw it very well. It's like that and sign. Oh my gosh, I'm doing horrible. Here we go. Here's an ampersand. So whenever you see those, it means it's a mixture. So right away, when I look at those, I'm going to go, okay, mixture. And same thing here. I'm going to go mixture. All right. Now the other ones are freed up. So let's look at this first one for H2O. H2O is a molecule. Let's see. It's a molecule and compound. Oh no, I put that in the wrong space. I have to rewrite that. Oxygen is an element and a molecule. Cannot be a compound because we've only got oxygen in there, no other element. So we said that water was a molecule and a compound. Let's see, carbon dioxide here would be a molecule and a compound. Gold would be an element. And we're not being shown that there's anything more than one atom that we're looking at. So we're not going to call it a molecule. So it's just an element. Nitrogen gas, I would consider it an element because it's just made of one type of element and a molecule. And this last one, carbon, is an element. And we can say an atom. It's not a molecule because we're not showing it's attached to anything but one other carbon. So out of here, this one's asking you which shows that which indicator does not show that a chemical change has occurred. So what you want to read this as is which one does not show a chemical change. So it can't be color change because during a chemical change, we have a color change. It can't necessarily be gas forming because bubbles are gas. And bubbles are a good indication of a chemical change. And a precipitate is also a good indication of a chemical change. So none of those three other ones, A, C, or D, would work. So we know that a physical change, which is a phase change, is not a chemical change. Because when we're looking at water boiling, for example, if we have liquid water and it becomes a gas, well, it's still the same substance. When you look at the composition, H2O here, it's the exact same as over here, H2O. So no chemical change occurred, it's just a physical change. All right, number 11. So a bicycle rusts, that's going to be chemical because rust is iron reacting with oxygen, giving you iron oxide. So when we look before and after, these have changed composition. So that's definitely a chemical change. A piece of chalk is crushed into powder. That's physical because all it is smaller pieces of the same substance. Marshmallows are roasted over a fire and turn black. That's a real key term here, turn black. So that means they were burning. So that's a chemical change. And if we look at this description for letter C, we saw a color change. So that's an indication of a chemical change. A, we saw a color change. That's an indication of a chemical change. All right, describe the accuracy and precision of these shots as they're being made. And let me open up another window. Give me a sec. Okay, so let's take a look at this. So accuracy and precision. If you're accurate, that means you hit your mark. If you're precise, you don't necessarily hit your mark, but all your measurements are close together. So if we have 99 out of 100 shots made, that would be accurate and precise. If 99 out of 100 shots were close to each other but didn't actually get into the basket, those would be precise because the measurements are close together, but not accurate because they didn't make it in. And if only 33 of 100 shots are made and the rest missed, not precise, we're going to assume they're not closely together. If they were closely together, then it would be precise, but in this case, we're going to assume that. And it was not accurate either because only a third of them made it in. All right, for these, I think you guys will probably need some of the most help. A block of lead has dimensions of those numbers, and the block weighs 1,587 grams. We're going to calculate the density. Thing that I like to do is write out the formula for density. Density equals mass divided by volume. So now we've got to figure out, do we have mass? Do we have volume? So yes, we've got our mass is 1,587 grams. But we don't have our volume. The way we can find our volume is mass times length times height. I'm sorry, length times width times height. Ooh, just making up my own unit here. So I plug this into my handy dandy calculator. And I get 4.50 times 5.20 times 6.00, and I get 140.4. And that means that's our centimeter cubed. Look at that. We took centimeter times centimeter times centimeter. Well, if we take centimeter times centimeter times centimeter, that gives us centimeters cubed. So now we've got our mass and our volume. We're going to put it in 1587 divided by 140.4. And I get something like 11.3. Don't forget your units, grams per centimeters cubed. And then circle it or put a box around it or something. Here we've got a problem that says 25 grams of iron shot, which is just iron pellets, is added to a graduated cylinder which starts off at that volume, and then when the shot's added into it, it goes up to this volume. So what we need to do is take our final volume and subtract our initial volume, because the displacement of water will tell us, well, how much volume was displaced by putting in an irregular object. The irregular object would be those beads of shot. So when we do the math, we should get 3.60, and you could do that in your calculator. So this is going to be the volume. And we are already given our mass, which is 28.5. So density equals mass divided by volume, which our mass is going to be 28.5 divided by 3.60. Sorry, I'm a little congested today. It's those wildfires. Some of the air quality has been the worst that I've ever tested in my yard. 7.6 grams per centimeter cubed should be your final answer. All right, so this student has unknown liquids, and we need you guys to draw how they would be layered in it. So we'll put our container here. And let's see, we've got different volumes and different masses given together with these. So let's take a look at how it's laid out, because it can be confusing. So fluid B has a mass and a volume of this. Fluid C has a mass and volume of that. And what you're going to end up having to do is calculate the density of fluid A, density of fluid B, density of fluid C, and density of fluid D. Sorry, we don't have a D. So you're going to have to calculate these three densities, and you're given a mass and a volume. You're going to take your mass divided by your volume for all of these. You're going to get a density, and whichever one is the lowest density will float on top of the others. So the one in between will go in the middle, and the highest will be on the bottom. And for these, I'll just talk through my solutions, because I already set this up for a student who came for tutoring. So you can just take a look at it. I'll point out a couple things to keep an eye on. First off, make sure you know what unit you're starting with. So this one said, how many days will it take for Mr. Aubin's hair to grow to Mr. Punkay's length? So it's asking us for days. We know that that's what our final unit should be. Now our starting unit has to be length. How many days will it take for Mr. Aubin's hair to grow to Dr. Punkay's length? So what is Dr. Punkay's length? It's 1.2 feet. So that's our starting unit. So 1.2 feet is what we're starting with, and what we're ending with over here is going to be days. So we need to find a conversion factor that will be converting in between those. So we're starting off with feet. We know feet should be the next unit on the denominator of the conversion factor next to it. So this is our conversion factor next to it. Below is the denominator, above is the numerator. So these units will end up canceling out because we're not asking for feet, we're asking for days. So we know that the hair grows 30.48 centimeters is equal to 1 foot. So the hair grows 0.42 centimeters in 1 day. Since we have centimeters up here, we need centimeters down here so they can cancel out. So look at the way we're doing it. We're going from feet to centimeters, then from centimeters to days. So we go down, up, down, up. So take a look at those units. Down, up, and we should get about 871 days. For this first one, the question is, well, if you have 320 grams of glucose, how many atoms? So our starting is grams of glucose that we're given. Our ending is atoms. So I put my 320 grams of glucose. Grams of glucose are our unit. So I just abbreviated GLU for glucose because I'm too lazy, and it makes it a little more complicated looking. So I take those grams of glucose and I convert it to moles of glucose. Then, once I've got my moles of glucose, I convert the moles of glucose to atoms. And in this problem, you're given that there are 6.022 times 10 to the 23rd atoms of glucose in 1 mole. So that's where we got this. These are equal. And same thing with this. These are equal. If we've got 1 mole of glucose, and is equal to 180 grams, those are going to be a ratio or a fraction that we put on top of each other. Remember, these fractions need to be true. They need to be equal to each other. Number 19, I take a little pride in because I made this problem up from scratch. And I think it's interesting just looking up data from the internet and just doing some calculations. So in 5 years, what volume of gas would you have farted? So we're starting with 5 years, and then it's asking for how many liters. So we know our starting unit is years, our final unit needs to be liters. So whatever comes up at the top as the numerator in our final conversion factor will be what this whole machinery spits out. So we go from years to days, from days to farts, and from farts to liters. So a easy way to check your work once you've got this set up, are these equal to each other? And I will say yes, because that's the information we got in the problem. Now, do the units cancel out? Years cancels out, days cancels out, farts cancels out, and we're left with liters. So yes, this is a correct setup. And it's nice to write it out this way because you can visually inspect your work and see if you did something weird. In this case, this is a little tricky. You had to go from, well, it's telling you how much will it lose in 1 day. So you're starting with 1 day, but it's asking you to convert to minutes lost in 1 day. So you have to take your day, convert it to hours, hours convert it to minutes, minutes convert it to how much you lose in each second. So this is where we have our 0.15 seconds each minute, but that answer didn't ask how many seconds, it asked how many minutes. So we have to convert it again from seconds to minutes, and we get 3.6 minutes. Ooh. For this one, draw the heating curve of ethanol and the cooling curve. Include the following labels. So for any heating curve, we're just going to be putting, let me get some of this junk out of the way. For any heating curve, you're going to have an X and a Y, and on the X you can put energy or heat or time, but we're going to say heat for our purposes. And on the Y you'll have temp or degrees Celsius. And usually when you draw a graph, it's nice to label it. We can say heating curve of ethanol. Ethanol is an alcohol. And we'll just draw a generic curve in here. Up, flat, up, flat, up. Now, once you've gotten to this point, now just put in your temperatures. So we're told here that ethanol has a melting point of negative 117, which is the same as the freezing point. So this is going to be our freezing / melting point, which is negative 117 Celsius. We're also told that it has a boiling point, so where it turns into a gas, of 78 Celsius. So right here, I would put 78. And then the cooling curve would just be the opposite of that. I'm not going to draw that out. It's just the opposite. So for the cooling curve, maybe I will draw it out. For the cooling curve, it's just the opposite. So you would start with a gas becoming a liquid. So it's just the opposite. If we put a mirror up right here, they should look like mirror opposites. And then, of course, you'll write your stuff in and identify the heating and cooling curve. Of course, I haven't put everything in here, but here you'd have boil. Here you would have freeze. Oops, you'd have boil. If you go to the right, you would have condense. Let's do it right, Patrick, so I don't tell students the wrong thing. So technically, if we move to the right, we'd have melting here, and we'd have freezing going the opposite direction. So I sort of put a heating and cooling curve together. Let's see. So make sure you're identifying your solid, liquid, and gas. So this would be gas, this would be liquid, this would be solid. We did boiling, we did freezing, melting point, melting, freezing, condensation. Yes, we did. Sublimation, that's a tricky one. That's going from a solid to gas. So things sublime, if they go from a solid to a gas, we did boiling, we did gas, we did liquid, we're good. All right, so for these, I'm not too keen on the graph that I gave you guys to look at, and I'm going to apologize for that. From the diagrams you drew, what state of matter, solid, liquid, or gas, will ethanol be at 22 Celsius? Actually, this one you could totally do with the graphs that you drew. 22 degrees Celsius is going to be in this range, so it would have to be a liquid. So you could either circle liquid or write in liquid. And for these, for 23 and 24, the table doesn't really, I don't like the table that much. Does ethanol have weaker, stronger intermolecular bonds? It has stronger because it's got a higher boiling point. Is it possible for ethanol to sublime? We're going to skip that. And we're going to skip this, really. The idea behind this question was, as we take pressure off of a gas, if we take pressure off of anything, we will lower its boiling point because we're taking that force off of it. But I'm not going to go into a whole bunch of detail about that. I know that was really confusing. And on the test, I'm going to skip over those questions for you guys. I know this was a long video. Tell me about it. This is my Sunday. I hope that this helps. As far as tutoring on Monday, we were surprised with the 3-hour meeting that's going to occur Monday. So I'm not going to be able to make my first tutoring time, but I'll be able to make the afternoon ones. Hope this helps.